dear students, how are you? I hope you are all doing fine. Today we are going to continue section 4 in chapter 11 with interactions. We have studied in our previous sessions the principle of superposition and the difference between constructive and destructive interference. I hope you have studied them well, and today we are going to continue about wave reflection. Have you ever thought about what happened to the motion of a wave when it reaches a boundary? You know the boundary, when it reaches a limit, when it strikes a wall. What happens to the wave? Will it come back to the opposite direction? Will it reflect? Does it depend on the boundary? So let's see. For example, here is a rope. Let's start from the left side. Here is a rope, and you are gonna make a pulse towards the right side, an incident pulse towards the right side, but be careful. Here this ring or the rope is not fixed, it's free. The boundary here is free. Free means that it's not that fixed, so that's why it can move up and down by pushing the wall towards that side. So it actually, yes, it happens. So when you push the rope making a pulse towards the right side, it makes the boundary move up for a while, hitting the wall or the post. Then when it comes back again, the wave or the pulse to the left side due to hitting the wall, this ring comes down for a little, down back for its normal position, preparing the pulse to return back again to its normal position at the opposite side. So this wave or the pulse is reflected now. Here is the incident pulse, but here is the pulse after reflection. So simply again, when the pulse reaches the boundary, the rope is free to move up as usual, and it pulls the ring up with it. As you have said, it pulls the ring up with it, as in the second one. So then the ring is pulled down back, okay, back down by the tension in the rope, causing a pulse to travel back. There is a tension in the rope, so by this tension force, the pulse travel back again along the rope to the left. So here is when the boundary is not fixed, is free boundary. So what happens to the pulse or the wave? The wave is only reflected to the left side. So what about if the boundary is fixed, like on the right side, fixed boundary? Can you see? It's different here. So what happens when you make an incident pulse towards the right side, like here? What happens when the pulse reaches the wall? When it strikes the wall, the rope exerts an upward force, because here is the pulse at the upper position from the equilibrium position. So, which exerts an equal and opposite reaction force on the rope. The wall itself, since it's fixed, so here is a fixed boundary. So the wall, what does it make? It pushes with an equal and opposite reaction force on the rope. So then what happens after pushing with an equal or exerting an equal and opposite reaction force on the rope? This downward force on the rope causes displacement again to the rope, but in the direction opposite to the displacement of the original one. So the original one will be upward or above the equilibrium position, and while returning back or while reflection, it will be in the opposite direction. The displacement will be in the opposite direction of the original pulse, not like this one. So simply we can summarize all this by, if the boundary is not fixed, if it is free, the wave will be reflected. The wave will be reflected normally. But if the boundary is fixed, like here, the wave will be reflected and inverted. So simply, at a free boundary, waves are reflected, and at a fixed boundary, waves are reflected and inverted. So after reflection, it will be inverted. Okay. So this is about wave reflection. So now let's see, if we have two waves, like in this figure, if we have two waves, okay, of the same amplitude, the same frequency, the same wavelength, are moving in different or traveling in opposite directions and interfere together, what happens? A resultant wave occurs. A resultant wave occurs. Again, when we have two waves of the same or have the same wavelength, frequency, and amplitude, are moving or traveling in opposite directions and interfere, overlap I mean, so the resultant wave is called standing wave. So what does it mean by a standing wave? Standing wave is a wave pattern that results when it is the resulting wave when two waves of the same frequency, wavelength, and amplitude travel in the opposite direction and interfere, like this one. So by the way, it consists of alternating regions of constructive and destructive interference. Do you remember the constructive and destructive interference? So the constructive interference, let me remind you, it is the interference of when the two waves have the same amplitude or the same displacement from the equilibrium position, while the destructive in the opposite have the opposite displacements from the one up and the other one is down, one left and the other one is right, have the opposite direction from the displacement or the opposite displacement from the equilibrium positions. So the standing wave consists of alternating regions of constructive and destructive interference. So here, if you can notice, here is a dot called node, and here is another one, here is another one. These nodes, these regions are called nodes, and at this position or at this point, what happens? The displacement equals 0. There is no displacement at these points. Okay, what about this point or this region, which is called antinode? Antinode means the position or the point at the halfway or the midway between two nodes. But here, can you notice that the displacement here is maximum or the largest displacement from the equilibrium position, I mean. So the difference between node and antinode, the node is the point at which the displacement equals 0, no motion, while the antinode, this is the point that halfway between two nodes and the displacement is maximum or the largest. So standing waves have both nodes and antinodes. Node means a point in a standing wave that maintains 0 displacement. 0 displacement at these points, nodes. While antinode is the point in a standing wave halfway between two nodes. Halfway between two nodes at which the largest displacement occurs, or the maximum displacement occurs at this point. So this is called standing wave. So let's see a short video about standing wave to be more clear. Here you can see, yes, here is a fixed end and the fixed end at the other side. And by the way, the fixed end or the boundary here is fixed. That's why the coming or the reflected wave is inverted, as you see. Back again. Yes, it's back again. It's reflected but also inverted. Why? Because the boundary there is fixed. So what about if we increase the number of waves? If we increase the number of circles, the vibrations, which is called first harmonic. First harmonic means only just one push, just one pulse. So one antinode. There is two nodes, but only one antinode. This is called first harmonic. So let's see by vibration of the rope. What about if we increase the number of circles? Yes. Now, second harmonic means it makes two antinodes. Can you notice? One here and the other one is here. So now we have two antinodes and how many nodes? One fixed, two second fixed point, and three. So we have three nodes but two antinodes. So they are, yes, as we have said, node, 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 and in the middle between them, in between, there are two antinodes. What about if it is three? Which means more frequency, more, yes, faster, faster, moving it faster again. So it makes three. 1, 2, 3 antinodes. 1, 2, 3 antinodes. That's why it's called third harmonic. More faster means more vibrations, more circles, more frequency. By increasing the frequency, the wavelength decreases. By the way, fifth harmonic, fifth means 5 ones. 1, 2, 3, 4, 5. 1, let's count together. 1, 2, 3, 4, 5. 5 antinodes. So that's why it's called 1, 2, 3, 4, 5. This is called a standing wave. Standing wave. Again, back again. More faster. 6. Now they became 6. Again 7. Now it becomes more faster. So the number of circles increases, the number of vibration increases, so the frequency increases, and now it becomes 8. More and more fast. So this kind of wave is called a standing wave. Back again. So back again to this point about the standing wave. Yes, we have said the difference between node and antinode. So for example, in this example, here is a wave, here is a rope, as we have just seen now at the video. Here is a rope, its length is L, okay, and by the first one, the first harmonic, it makes just one antinode, just one antinode and two nodes, and by increasing the vibrations, as we have seen since a while, we have two antinodes, 1, 2 antinodes and 3 nodes, and by increasing it will be 3 and so on. So now if we have considered only certain, by the way, only certain wavelengths produce standing wave patterns. This is called the standard standing wave patterns, by this way, by increasing the frequency. And we have said before that the frequency and the wavelength is inversely proportional, or inversely proportional to each other. I mean, by increasing the frequency, the wavelength decreases. Do you remember the V, the speed of the wave, equal F multiply lambda? So only lambda equal V over F and F equal V over lambda. So F and lambda are inversely proportional to each other. So what does it mean? It means by increasing the frequency, by increasing the number of circles or the number of waves, the wavelength decreases. So for example, if we have said that here the wavelength equal 2L, the wavelength here equal 2L, double the length of the real string, the original string. So here the wavelength equal 2L. What about if it is divided into two waves like this? So the wavelength will decrease to half. So each one will have its wavelength will equal to just L, not 2L but just L. What about if it will be 3? We have to make these 3 waves, or this standard wave, this pattern to be 2L. So each one will be 2 over 3. Yes, 2 over 3. The lambda here equal 2 over 3 of the L. So again, if the real length of the string equal L, so here in this pattern, the first standing wave pattern, the lambda equal to L. It's a given that the wavelength here of the standing wave equal to L. And by this way, if it becomes by this way 2 harmonic, it will be just L, and if it will be by this way, it will be 2 over 3 L, and so on. What about if they are 4? Each one will be 1 over 2. Yes, 1 over 2, 1 over 2, 1 over 2, 1 over 2, and so on. in order to be 2 at the end. So at the end of the string must be nodes because these points cannot vibrate. Be careful. These points, the nodes, cannot vibrate. Always nodes cannot vibrate. So it will be always at the end of the string. So at the end of the string must be nodes. Why? Because these points cannot vibrate, and the standing wave can be produced by any wavelength that allows both ends to be nodes. So the most important one, that the two ends of the string will be nodes. Okay, so this is about the standing wave. Another example. Here we have on the left side, this photograph or this picture shows 4 possible standing waves. 4 possible standing wave like the previous one, but here 4, yeah, this is the 4th one, a new one. Okay, so here there are 4 ones. So this is 4 possible standing waves that can exist on a given string, and on the right side just the second one, just this case, the progression of the second standing wave on half circle or half a cycle. What does it mean, 1/2 a cycle? Do you remember the time taken by making a complete cycle? What does it mean? It refers to what? It refers to the period. Yes, we have studied before in the simple harmonic motion and again in the wave motion. So in 1/2 cycle means when t equal half t, when the time equal half time period, t capital. T capital refers to the period, as we have said before. So during 1/2 a cycle, what happens to the second standing wave? For example, at the beginning, when time equals 0, there is no time at time equals 0, the wave will be by this way. Here is antinode, here is antinode, and 3 nodes, as we have said. Okay, and after a while, after passing a little time, like 1/8 t, it will be like this. The wave or the pulse move like this in the right direction, to the right direction, but it will be more flattened, more flat. Okay, until it becomes like straight, like parallel to the equilibrium position, and after hitting the boundary or after hitting the wall here, it returns back again. It returns back again to the opposite direction, reflected back again, and then after the time becomes half the cycle, or after the time is done, it will become again like the first one, but in the opposite direction. In the opposite direction, it means it reflected. Okay, so this is the for an example, yani this the second one. What happens to it during 1/2 a cycle. So by this way we have finished section 4 of this chapter, and we have finished all the chapter since it is the last section in this chapter. So we have finished chapter 11. Please study it well and be ready for a revision in our next meeting. Thank you and goodbye.